Hello, everyone. This is my talk about virtual acoustics and how you can recreate the natural phenomena of sound propagation in the digital domain. So just a quick introduction before we begin. My name is Aidan Baker. I independently run an audio software business called Lese, where I make audio effects plugins, and soon we'll be releasing acoustic simulation software. I also work with other audio tech companies, with the current ones being Relab Development and Audio Thing. So what initially got me into audio programming was that I have been into making electronic music for quite a long time, since I was about 10 years old, and I went to university for a music production and recording oriented degree in Montreal, and one time, really late at night in the old city, I was walking through the empty streets and just clapping, as you do, and listening to how my claps sounded in entirely different streets and tunnels, and how wildly different it could sound when all I did was move one step to a slightly different position. So I kind of had an epiphany regarding this. There has to be some kind of way that you can simulate all of this digitally, and I spent the next few years learning how to program, reiterating some of my early plugins a dozen times over before they were released to the public, until I got to a point where I was confident enough in both my mathematical abilities as well as my software development abilities to set out on what I considered to be my big idea at the time. So I realized that there would probably be a lot of benefit to having something like this. You can have a conventional digital reverberator that already kind of does this, of course, or you can have a convolution reverb plugin that has a lot of different impulse responses that are actual recordings of real spaces that can accurately simulate those spaces, and all of that is fine, but what if you were a game designer and you wanted to get an accurate acoustic representation of some amazing level at a bunch of different positions? What if you wanted to do this in real time? A traditional digital reverberator cannot do this. What if you were working on a movie or a TV show and you wanted to correctly remake the acoustics for some CGI scene that doesn't actually exist? You cannot do this with a traditional digital reverberator. What if you were an architect and you wanted to try and simulate how the $1 million acoustic music studio that you were designing actually had the proper acoustic responses you wanted in the right spots before you sent it off for actually being built? Traditional digital reverb won't help. And finally, what if you were a music producer and you wanted to make a reverb that nobody has heard before? There is not a convolution reverb impulse response in existence that simulates what it might sound like in a mile-long tube made out of carpets, but with acoustic simulation, there certainly could be. So, before we get into everything, let's just go over the scope of what I'll be discussing and what to expect. So, I'll mostly be looking into the game sound and music production aspect of all of this stuff, as we will be going over how you can work with virtual acoustics in different complexity levels so that you could implement a system that would work in real time, no problem. And using the same methods with different high-level parameters and constants, you could also implement it in a high-quality offline system. In the game sound and music production aspect, there is also a lot more dynamism to what someone might want to do, as opposed to film where exclusively offline rendering would be expected. There's a lot of diagrams that go over things, as well as some 3D renders that I've done to help explain some of the more mathematical concepts. And also, there are no code examples. And the reason for this is that when I was trying to put everything together for this talk, I found that everything is either so high level that the code basically reads as use an algorithm and then you process its output, or they're so low level that the code example would be hundreds of lines and it would be too long to go over in our allotted time. Yeah. So finally, anything that involves showing off how this stuff works was done in various versions, early beta all the way to MVP, of a piece of software I will be starting to release soon, hopefully, called Impulse, which is for doing offline impulse response rendering with three-dimensional geometry. Basically, think of all of this talk as more of a math and physics lecture than anything. We do go into how to process what we get from our algorithms eventually, but it is still just suggestions of how to go about doing it rather than specific instructions, as implementations of virtual acoustics can go in many different directions. So, primarily, in a game sound environment, we need to consider the resource budget. In a video game's context, the resource usage, both CPU, memory, and disk-wise, need to be low comparatively versus everything else. And additionally, the resource budget for this particular element of game sound would only be a fraction of the overall budget. Next up, the acoustic simulation needs to sound accurate to the user based on the current environment, or at least accurate sounding, and we'll touch up on that later. Finally, and this is primarily on the development side, any sort of program that would implement an acoustic simulation system should be easy to work with, i.e. a somewhat simplistic API. So the big question now is, how do we actually do all of this? The answer to this question is by utilizing propagation modelers. Specifically, these are all tuned in a way that makes them into sound propagation modelers as opposed to other kinds of propagation models, mainly where you could use ray-based methods for things in like pre-rendered computer graphics, and wave-based methods might be used for doing things like Wi-Fi propagation modeling and aerodynamic simulation. Yeah, and in this case, it's all about the constants utilized in relation to the model as well as how we utilize the output that these different algorithms give us. So we will mostly be looking at the ray-based methods in this talk, mainly because my personal research implementations are all ray-based, but also because doing something like this is in a wave-based system is a more computationally intensive process, and we'll go more into that later. So these are the two methods. This is the wave-based. Yeah. So the first thing that we'll be going over is the ray trace method. Ray tracing is exactly what you think it is, but it's just not for computer graphics, in this case at least. In our case, we implement things a little bit differently. Instead of a camera, we have a listener, and instead of a light source, we have a sound source, or multiple sound sources. While it may seem like this method would not yield accurate results in the specular sense, i.e. without modeling any sort of diffusion, this method is actually very accurate. And in fact, any kind of wave or particle with linear motion can be simulated accurately with ray tracing, such as modeling different electroacoustic phenomena. So, so this is an example of a ray-traced image of the Utah teapot rendered in Blender. And what we have here is an example of that same teapot mesh, but with an acoustic ray tracing simulation filling up the volume of the teapot in a beta build of my program Impulse. So you don't see the handle and spout. They're not filled because the Utah teapot mesh has overlapping polygons inside that wouldn't let rays pass through it. But if you look closer, you can see the individual rays. And you can also see one section here where the red is a bit brighter than the rest of the volume. And this is where the sound source emission occurred. So instead of it being a light, it's a sound source and it's emitting in all directions. So we have the workflow process to doing acoustic ray tracing here, and it's quite simple. The first thing we need to do is the casting step. Basically, we generate emission vectors that will emanate from an acoustic source. The way that these rays are calculated can be entirely random. They can be deterministic or anything in between. In my program's case, in lieu of casting rays randomly like this, i.e. getting 3 random values for the x, y, and z of the vectors and then normalizing them, I generate what is referred to as a Fibonacci sphere like this, where you give it a number of rays and you get n rays, which are almost totally evenly spaced. And this allows you to have much more even emission. If desired, you could also take your rays and wrap them into some kind of data structure where you could have an initial energy value. So you could have another function on top of the emission that could simulate sound source directionality. Moving on, the next step is the tracing step. Essentially, we check for intersections against the scene's geometry and we reflect off of it. And we add another ray segment to a larger acoustic path whenever we do this. We also check for intersections with the reflected ray segment as well, and we do this recursively up to the trace depth, or until we get below some predefined energy threshold, so that modeling a space where the geometry would have high levels of acoustic absorption, such as a soundproof chamber, we won't be wasting time tracing sections of rays which would ultimately be inaudible, as we would be checking if the energies are below that threshold whenever a intersection against scene geometry would be occurring. So finally, we have the intersection step for the listeners. All that we do in this case is check every ray segment of every traced acoustic path against given acoustic listener volumes, i.e. just checking if a ray intersects with a sphere, and then we take the intersection distance and incoming vector, and we use it externally in some kind of delay processor. More advanced simulators may also take things into account like the number of times reflected or air absorption estimation. So we have some glaring pros and cons of the ray trace method, of course. The main pro here is that the system is very fast. When we leverage dedicated ray tracing libraries like Intel's Embry, we can cast tens of millions of rays per second, and on a GPU it could likely be at least an order of magnitude more. The ray trace method's complexity can also be easily predicted. Simply put, the reflection depth multiplied by the number of triangles multiplied by the number of rays approximates your complexity. This is assuming that no optimizations have been implemented, though. Adding something like a BVH or an octree to optimize the geometry intersection test would speed things up, of course. And parallelization is also pretty simple with the system, considering that these rays are tracing in a way where the results of the rays are not interdependent with one another. We can do things like the following, where in this case here, in this case here, we are tracing rays 0, 1, 2, and 3 on one hardware thread, while ray indexes 4, 5, 6, and 7 are being processed in parallel on another thread, with the same geometry being used on both. In a real-world implementation, obviously, there would be way more rays than this, and there would be way more threads, and they would just be in larger chunks. So now we move on to the cons. A large con of this method is that the fact that the chance that a ray may intersect with the listener is relatively low based on volume, and the chance gets even slimmer as the overall volume of the simulated space increases, because a listener is a predetermined volume, and the chance that it could be in that volume decreases, obviously. And the other major issue is something that I've coined the wavefront issue, wherein essentially low-order rays that intersect with the listener, especially the direct source-to-listener rays, will all hit the listener at nearly the same time, and you need to compensate for that. This diagram here helps to visualize the wavefront issue. 9 rays are being cast from the acoustic source, and 7 of them are intersecting with the listener. While the middlemost ray is intersecting through 100% of the circular volume, the rays on the edges only merely graze it. So you will need to take this into account with some kind of attenuation value that's calculated during intersection, based on how much of the volume is actually being intersected. Okay. So next up, we have the second ray-based method, the beam tracing method. Beam tracing is designed specifically for handling perfectly specular reflections off of surfaces from a starting point to an ending point, or in our case, a source and a listener. Beam tracing, unlike ray tracing, does not generate any rays which would be potentially unused. So while we don't have to worry about having an intersection step in the workflow for a beam tracer, we just have to run the algorithm directly. So beam tracing here, yeah, we don't need an intersection step. So beam tracing essentially works by finding mirrored positions or image sources of a source point in arbitrary geometry. And for doing more complex reflections, it will handle doing this recursively, internally. There is also another method which finds image sources in a different way, which is called more directly the image source method. However, it is not as computationally efficient as the beam trace method. So what I mean by finding mirrored positions is essentially something like this. Imagine if you were in a room and every surface was a totally smooth mirror. You see in this room a point in space, maybe it's a ball or something as it is here, and you can see the ball's reflection on some of the mirrored surfaces. These mirrored positions are the reflections where specular light is reflecting from, off of the original source point. The transmission of light in this case can once again be utilized in a sound-related application. So visually looking at the image sources in the render simplifies things, but getting the actual paths is a bit more involved. In a basic sense, the simplest method of image source reflection off of a single plane would look something like this. The angle of incidence, i.e. the angle against the geometry created by the incoming ray, is always equal to the angle of reflection, the angle of the reflected ray off of the geometry. Of course, modeling a reflection like this with a simple flat plane could be modeled without the image source, but the utility of an image source in figuring out these reflections is better visualized with more arbitrary geometry. So here, this is an example of using an image source modeling with arbitrary, albeit 2D geometry. We only modeled the first order reflections in this case, and 3 of the 4 possible reflections are valid while 1 is not. The topmost side surface's reflection is invalid because the reflection that could be generated is outside of the 2D reflector's domain, and it's outside of the space entirely. In second order and higher reflections, what happens is that from the initial point of reflection, it then attempts to basically do what it did in the first reflection, i.e., try to see if the point where it's supposed to reflect actually exists on a surface, and this occurs recursively. I would show what this looks like when there are a lot of image sources present in an image, but it would probably be incomprehensible as the number of image source positions goes up exponentially with each order, and we get into that right now. The main pro in direct comparison to the ray trace method is that since all of the rays that this algorithm will generate are paths that are from the source to the listener, we don't need to worry about an intersection step. And subsequently, we don't need to worry about any sort of compensation due to a massive amount of rays that the listener might be intersecting with in the early reflection orders. What you have is what you have, basically. Another is that this method is totally accurate. When we do intersections and tracing in the ray trace method, we are intersecting with a volume. It's highly unlikely that the intersection would occur directly through the exact position that the center of the volume is, but in this case, that's exactly what we get. The origin of the first segment of the acoustic path would be at the source, and the endpoint of the last segment would be at the listener. And another thing to consider is that once these image source positions are calculated, we don't need to calculate them again, unless the image source position or geometry changes. If you were working on, say, a video game where you had static sound positions, but a listener that was able to move around in a scene, then you could, for instance, calculate all of the image source positions for the sound source at the initial runtime, and then get the rays whenever you wanted to, and then calculate reflections from there. This method would be much more resource efficient than recalculating everything every time you needed it. So, next up, the big con, and really the only con that I can think of with this method, is that as the order increases, the amount of memory used increases, and the amount of time that it takes to calculate these image sources increases, of course, and it increases dramatically. So the following here, this is a graph of a batch of tests that I did to demonstrate how long it takes as the order increases. So these were done on a desktop that could be considered mid-range when it was built about 5 years ago. Each orders test was done 4 times, and the process times were averaged to get our final results. Also, the geometry that was used was just a simple cubic room with 6 faces. So orders 0 and 1, as you can see here, were immeasurable with my method of measurement. Both of them took a millisecond or less to calculate. Every order up to 5 took under a second to process, but it gets worse from there. Here is the updated graph of how far up I went. You can't even see order 5's time anymore. We see a complexity growth where processing time roughly increases threefold with each increment that the order increases. The 8th order test took about 90 seconds to perform on average, and the 9th order test took about 1.5 minutes to perform. I only really bothered with processing the 10th order test once because it took so long, but as you can see here, it's very high. The elapsed time was over 311,000 milliseconds, or a little over 5 minutes. And keep in mind that this is just for a cuboid room. One thing to consider in regards to these tests is that they were done without any kind of real compiler optimizations, i.e. not in debug mode. But the point still stands that this method is largely unsuitable for processing higher ordered reflections, and this also can't be parallelized as far as I'm aware, so there's really no help there as well. Yeah. So, considering the fact that computing high-order reflections using the image source method is not feasible, there is one way to somewhat easily calculate image source reflections, but only in a room that is considered to be cubic, i.e. this will not work in any sort of arbitrary geometry. So the first step here is to figure out the depth that you want your reflections to go to, and then we generate a sort of permutation table, which will ultimately represent the reflection depths on each axis. To help this make better sense, here's an image of what a permutation table would look like for the direct sound source, 0, 0, 0, forced order reflections, which are 6 of them for each side, and as well as a few example second order reflections. We don't include all of them for the sake of clarity, of course. In actuality, the number of second order reflections is about 18. And with third order reflections alone, the possible permutations is 36. Going up, the number that we add to the table as the order increases gets higher each time. I made an audio plugin called Aidan that uses this method to render impulse responses and also simulate early reflections. The depth that we support computing up to on it is 40. And if I recall correctly, the amount of permutations that we get from that is about 30,000. Yeah. So the way this table works, so each possible image source position. And the way that this works is that as the order increases, we will figure out every possible combination that we can fit the absolute sum of the current order into the 3 axes. So what this actually represents is pretty much a multiple of how many reflected rooms over the ultimate image source lies. So for a first order reflection, it would look something like this. So in this case, we're doing the positive x-axis reflection, the first in our permutation table. And for a second order reflection, it would look something like this. In this case, we're reflecting the second order reflection in our permutation table. It's 1x over and then 1y over. And once we have these figured out, all that needs to be done to figure out the location of the actual reflected source is to take the position of the original source. We mirror its values depending on the axis or multiple axi that it should be reflecting on. And this method assumes that 0 is the center of the space. And we translate each axis based on the given dimension of the space at that axis. So if we had a sound source at the center of the world, and we were reflecting on the positive x-axis in a space that is 10 meters on all dimensions, or 5 meters in each direction from the center, the reflection would be located at 10, 0, 0 if it was 1x translation. And if it was reflecting on the positive x-axis twice, then the reflection would be located at 20, 0, 0. Once that is completed, all that we need to do is measure the distance between the listener and the original space to the reflected position, and we use that to calculate a delay time. One thing to note with this method is that the permutation table is another thing that doesn't need to be calculated explicitly at runtime. You could just hard code these values into the binary if you really wanted to, as they will always be the same in every application using them. Unless you wanted to set up some kind of system to, say, explicitly limit the amount of reflections on the floor and ceiling or something similar. So, now that I've gone over all of the typical ray-based methods, we should get into how these rays actually get processed into something that you can actually hear instead of just existing as abstractions. Consider what we want from a high level first. We need to take the rays, compare them against the speed of sound and the sample rate that you want your end result audio file to be in, and we determine the delay at which your audio will be at using these two factors. So the function for doing this is very simple. It's just your ray's distance in meters, the speed of sound in meters per second, which is usually 343, but in actuality it can vary based on temperature, pressure, and humidity, and we multiply that by the sample rate. Secondly, we need to apply attenuation based on your sound ray's distance from the listener. Assuming that the sound source is emitting evenly as it spreads, we can model this easily by taking inverse square law into account, which states that as the sound travels through space, its energy dissipates at a rate of its original intensity, divided by, So this is the function. Its energy dissipates at a rate of its original intensity divided by 4 times pi times its new radius squared. This means that the energy dissipates pretty quickly. So additionally, we need to attenuate based on all of the surfaces that the acoustic path has reflected against. In an ideal implementation of this system, the acoustic ray that you're processing would have this value, or multiple values if desired, if it's in multiband, stored alongside the ray's cumulative distance. Also, if you want to, you can, if in a multiband implementation, determine the effect that the motion of the air itself would have with attenuating your signal's higher frequencies. The way that this works is by implementing Stokes' law, which is a formula for determining frequency-based attenuation of sound in a Newtonian medium such as water or air. And this is the formula for doing it. It takes in some special constants that you probably aren't used to, such as the medium's dynamic viscosity coefficient, as well as the fluid density value. And these can just be stored as constants unless you were trying to make something with really in-depth controls. What we get out of this value is an attenuation coefficient that, when it's multiplied by the ray's cumulative distance, it gives you an additional value that you can use to attenuate a single band of your audio. If you were motivated, you could probably try and implement air attenuation accurately using this formula as a basis with some kind of IIR filter, but personally, I haven't tried doing that. Next up, we need to account for the fact that sound is supposedly reflecting against various surfaces by inverting its phase. You only need to do this in cases where the sound ray has been reflected an odd number of times, and I'll use, think about a one-dimensional wave as an explanation as to why that is. Essentially, the energy folds back on itself and inverts its energy value as it travels forward, hits the end, and then travels backwards in a reflection. And then when it reflects forward again, you're back to the way that it originally was because it reflected again. Thus, the reason for only needing to worry about this factor in odd-ordered reflections. Additionally, accounting for spatial encoding is pretty straightforward. And this section here is assuming that you have experience with ambisonics or spherical coefficients in general. All that we need to do is take the incoming vector, i.e. the direction that the ray was coming from when it intersected with the listener, and we use that as a basis for doing ambisonic encoding into a multi-channel ambisonic sound field. This would let you use it in multiple applications later on, such as a multi-channel environment, of course, binaurally, or simply decoded into stereo or even mono with the W channel of the sound field. Next up, we can look at the last method for doing acoustic simulation. The wave function, which is also commonly referred to as a waveguide or an acoustic FDTD, which stands for finite domain time difference simulation. Mathematically, these two models work differently, but the underlying concepts remain the same. Basically, we have a large three-dimensional matrix, or even higher than that if you really wanted to, matrix of nodes that work to propagate a sound signal through them, frame over frame or sample over sample. So, the interesting thing about this matrix system is that the node interconnection pattern does not need to be something conventional, such as where they would only be connecting on 6 sides like a cube. You can set up whatever you wanted and what was suitable for your application. So even setting up systems where different nodes and subsections of these patterns could have different connections than others. So the waveguide model works to do what the ray-based algorithms cannot, mainly handling wave effects such as diffraction and interference. So diffraction, of course, being where waves tend to bend around a boundary, such as a surface. Like in this picture from a bird's eye view of a ship getting hit by waves. Notice the waves curving around the bow and stern of the ship. And interference, like this, where waves in the medium would be affecting one another while traveling. You can't get that with rays which just bounce from one location to another and are not actually interacting with one another. So it's about interaction, basically. So now we can look at an example workflow for handling a wave function sound propagation simulation. Example is the keyword here, as the way you might choose to implement how the internal mesh is built might differ, and the way its node positions are calculated may be different. So the first step is to prepare the acoustic geometry. Ideally, the space should be turned into something that could be considered watertight, meaning that the space would contain a valid volume for processing in the next step. Usually, this would just be done by simply converting the space over to a simplified rectangular representation of the space, basically just a bounding box that should be aligned to the rotation of the model as close as possible. And this will be the volume in which the simulation occurs. Of course, it's not likely that all of this volume will be utilized in the final simulation. The surface nodes will reflect sound in a way that energy remains inside of the grid, and edge nodes will absorb it entirely as if it just kept on going, or you had an empty space, like an open window or something. So the next step is for the creation of the actual mesh. This step just involves the creation of the mesh that sound will be propagating through as the simulation runs. Primarily, we need to determine the locations of the nodes based on the sample rate that we wish to operate off of. As said before, edge nodes will be placed at the boundaries of the simulation that will absorb all acoustic energy. Surface nodes will perform multiband attenuation on the energy that collides with it, and air nodes will simply just propagate the signal through themselves. Finally, all that we need to do now is excite the simulation. All we need to do is feed a positive value into one of the nodes and then just run it as it propagates, frame by frame, and then sample by sample. And what we do at the end is we just like sample the values over time from one of the nodes or multiple nodes, frame over frame, and then we have an audio file, basically. Yeah. So I mentioned that we would be handling multiband absorption with acoustic materials in the workflow for this method, but there are some quirks with implementing materials in these sorts of algorithms which don't need to be considered in the ray-based algorithms. When a propagated, so when a propagated sound hits a boundary, we don't have a set of multiband absorption coefficients that we would be using in a later process like we would in ray-based algorithms. So in this case, what we would do is implement an IIR filter on each of these surface nodes. The IIR filter would behave the same way that a normal IIR filter would, where its coefficients will be calculated with the sample rate that the wave function simulation is running at, and its frequency attenuation would attempt to match the absorptive qualities of the provided acoustic materials multiband coefficients. When a node collides with this boundary over time, it would filter the incoming signal when it travels through and bounces off the surface node. The way that you implement this filter is, let's just say that that's an exercise left up to the listener. I haven't really done much of that. So now we can look at the pros and cons of the wave function method. The big pro, of course, is the ability to simulate various wave phenomena as described in its introduction. Rays which are being cast do not affect one another, unlike this simulation where all of the nodes are processing and propagating in tandem over time. Another is its relative simplicity. Propagation between nodes which are not trying to act as surfaces or edges, also called boundaries, only involves some really super simple copy, add, and multiply operations. And the last one is that it's very easy to use with actual processing, as opposed to having to take each of the rays in the ray-based method and process them individually based on data structures that you get that the models spit out. The only thing that you need to do with the wave function is measure sound pressure at any one of the simulation's nodes. Now, there are some cons to this method, however. One big one is the density of nodes required. The algorithm's complexity can be measured by the volume of space to be computed, as well as the sample rate which would be desired to process in. If you were processing at 44.1 kilohertz in only 1 cubic meter of space, you would require 44,100 cube nodes, or about 85 trillion of them. The density issue could be mitigated, however, by doing something like reducing the sample rate when processing and upsampling to your actual desired sample rate later on, where you would only be capturing low-end responses accurately. Another issue, yeah, that's a big number. Another issue is what I refer to as the emission error issue, where rays are only able to emit and disperse throughout the medium over time in the same fashion that it allows for based on the interconnection of the nodes. If you had a node mesh where nodes were, what am I trying to say? Were connected on all 6 sides like a cube, then the system would only be able to get to the nodes around it that are not interconnected, the diagonal ones, in the second and third processing steps. Additionally, if you wanted to try and mitigate this by changing the node structure so that the connection pattern is more spherical, i.e. connected in more of some kind of tetrahedral mesh structure, That would help with this problem, but you would ultimately be creating more interconnections between nodes and thus requiring more calculations, as there would be some propagation directions that the signal will be traveling through. So now we've went over how to realistically simulate the early reflections of a space with propagation modelers, and while you could try and use these systems to model reflections beyond only a few dozen bounces, there are much more efficient methods for handling late reflections. So, as opposed to doing anything highly elegant, the method that I use in this aspect of acoustic simulation just involves taking a conventional feedback delay network. We tune it so its internal delay attenuations match the desired RT60 profile of the room, and even taking its internal delay line time values, and we try to match them to the early reflections. So we'll have that, and then they'll remain co-prime of one another so they don't overlap during processing. The big question, though, is how do we actually figure out what to use for that? So the method to do this involves first calculating or estimating the volume of the space and trying to get a good average of how the multiband attenuation behaves based on all of the surfaces in the scene. We then take the volume and the set of absorption estimates and use the Sabine formula for each band to get a reverberation target in seconds. The delay line can then have its gain set by figuring out the relationship between how long it takes for a single delay line to loop and how much we should be attenuating at each loop so it will reach negative 60 decibels in gain within the allotted RT60 target. You could also easily set up a multiband crossover filter with multiple reverberators to do this for multiband reverberation as well. Of course, yeah. So in terms of a conclusion, we went over 3 of the most commonly used methods for simulating sound propagation. All of them have their strengths and all of them have their drawbacks. Ideally, the best form of an implementation for your application needs to take in the most important factors and build them out from there. Most implementations that are already out there will either not be good enough or will use too much CPU for whatever it is you're trying to do. If you want to do incredibly realistic simulations without concern of it being in real time, you could probably do well with a parallelized waves-based simulation on a powerful computer. But if you wanted to do something that's convincing without having to use too many resources, you have ray tracing methods as well as the optimized pseudo beam tracing method described earlier. Beyond the algorithms as well, you need to consider how you want to actually treat the DSP side of things. Do you want nothing more than delay and distance attenuation, or do you want comprehensive spatial reflections and realistic frequency-aware material simulation? All of these things need to be considered in your own implementation of virtual acoustics. So, all in all, I hope that even though a lot of this talk exists in a very abstract sense, you managed to gain a good understanding of what it is that I'm so interested in. Additionally, if you would like to participate in the beta testing of my upcoming acoustic simulation software, you can email me through impulse@lese.io. By the time this recording gets put on YouTube, it will probably already be released in some capacity, though. Additionally, with the slides, you will find a list of sources that I went through in doing extra research for this talk that range from things like interactive demonstration websites to GitHub repositories to different research papers. So thank you all for your time, and that is my talk. Thank you.